instructors for ERS International. Today, the subject we're going to take a look at is ventilation practices at confined space incidents. Prior to this module here, you're going to want to make sure that you have reviewed and are refreshed on the two previous modules relating to air monitoring and the setup of the air monitor and the 4x4 air monitoring procedure. That will put you in good standing to move directly into the ventilation practices. We'll review in this segment how to set up the equipment, problems associated with ventilation, and some of the other facets of that subject. So let's take a look. All right, let's take a look at the ventilation equipment that we're going to be making use of during our confined space emergencies. The three major components that we want to take a look at are the ductwork, the fan itself, and the power supply or the extension cord portion of it. We'll start by talking about the extension cord. As part of this kit, you're going to need to have an extension cord. The extension cord that you keep on your ERT cart should be one that, of course, is long enough to typically reach an outlet, keeping in mind that many of the confined spaces won't have an outlet right nearby them. A classic example of that would be something like a manhole where there is no other electrical source nearby. So it'll have to be long enough. It should be of adequate size to run the fan that you're using. And then a lot of plants have outlets throughout the facility that are not a standard household type outlet, a three-prong outlet. They may have some of the other more industrial type connections in them. So an adapter between the plug that's on your fan and an outlet that you might use in the plant is also part of this, should be included in the kit. Other teams also are considering adding a generator to their cart for those scenarios where an outlet is not readily available or the outlet has maybe accidentally gotten turned off as part of your energy control operations and thereby taking away the power source for your fan. So a generator is a good alternative. In either case, it acts as a nice backup to the primary power source so that you can keep your fan working no matter what happens. Let's take a look at the fan itself then. There are many, many makes and models, different styles of fans out there. The squirrel cage blower type thing is a fairly common fan that we'll see in the facilities. Very, very few, if any, of the plants have intrinsically safe fans. In other words, they're not meant for use in an explosive atmosphere or flammable atmosphere. They're just meant to provide that fresh air, to circulate fresh air into the space. Most of the fans that we'll run across have the option to either attach ductwork to the output side of the fan, or it can also be attached to the intake side of the fan, depending on what we're going to do. Most of the time, probably 95% of the time, we're going to be attaching our ductwork to the output side of the fan. Also want to recognize that most of the fans have some kind of an on-off switch, in this case located right down here in the front. It can take a couple of different forms. One particular version of fan has a two-position switch for the on-off switch. There's a high and a low speed. And for rescue operations, we want to be running the fan in the high speed position to maximize the volume of air that's running through it. So power cord assembly, we want to make sure we identify that, the on-off switch, and then the fan itself needs to be, we have a way to connect ductwork to it. The other thing we're going to be needing here in just a moment is some duct tape, and we're using the duct tape for two reasons. One, to ensure that the ductwork that we attach to it, this flexible ductwork we see here, doesn't accidentally come loose and potentially fall into the hole, and also so that it minimizes any leakage in there to maximize the air that's being introduced in the confined space. So not a bad idea to attach some duct tape right to your fan so that it's readily available. You're always going to have it. You don't have to be looking around for it during the emergency. And then you can just simply, I'm just using a small piece of tape here. I can just simply break the tape loose, and I have the tape available to make my connections. Okay. So there's our fan. Keep in mind, again, worth repeating, almost none of the fans that we're going to encounter in the plants are explosion proof. So we don't want to be operating them in a flammable or potentially explosive atmosphere. The way we utilize the fan to get the air into the confined space, or more correctly, into the near the head of our patient, is the use of ductwork. The ductwork comes in a variety of lengths. 20 or 25 foot is pretty common. Almost all of them will have some kind of a cinching strap on the end that we can use to make that connection point. And so as the people of the team assigned to set up the ventilation, simply just ensure that the strap is opened up and then pass it around the discharge on the fan, or the output side of the fan. Most of the time this is a bit of a snug fit. It will take a little fussing to get that on there. So as I said, we want to get our ductwork detached on the output side of the fan because we're going to be trying to blow fresh air into our confined space. We have the ductwork attached, and we're going to take the strap and cinch that up, and then we're going to make a more secure, permanent, airtight connection with the use of some duct tape. Just wrap it around a couple of times. To again ensure that the ductwork doesn't come off and that we minimize any air leaking through there. Once the team gets the fan set up, the last step that they should do is to test the fan to make sure that it in fact is working, that they have the hose hooked up correctly or the ductwork hooked up correctly. So we'd connect the fan to our power source, flip the switch on, make sure that air is coming from the ductwork and in fact is blowing out. This is the most efficient operation for the fan, or the most efficient setup. In other words, it will move the most air in this configuration. When we try to do it opposite, when we try to draw air out of a confined space, the efficiency of the operation goes way, way down. This is how we get the most fresh air to our patient in the confined space. Okay, I mentioned that we want to set up our fan for positive pressure ventilation, or in other words, where we're blowing air into the confined space. I want to just demonstrate real quickly why, or more correctly, how this is so much more efficient than the negative pressure ventilation, or where we try to suck air out of the confined space. So on the floor here we just have a medical glove inflated, kind of like you might blow up a balloon, and we're going to use that as a demonstration or a model of an air molecule that we're trying to move around in the confined space. So notice I've got the fan running, connected to our ductwork. When I direct the airstream at that molecule of bad air, you'll notice that even from 4 or 5 feet away, I can move that thing and I can blow that thing several feet across the floor. So I'm able to influence its movement at great distance. We'll change the setup here a little bit, and we'll do some negative pressure ventilation where we try to draw that air out, and we'll see the difference in how efficient this is. All right, here we have the reverse setup where I have the intake hose connected to the side of the blower, and I'm drawing air into this end of the tube. Looking back at our example or our model, we have our molecule of bad air that we're trying to move around in that confined space. And here we are roughly about 3 feet away from that molecule of air, using the same blower, the same ductwork arrangement, and it's not moving that molecule of air. As I start to move this in closer, now we're about 2 feet away, or a little less than 2 feet, and I'm just barely starting to get a little movement out of that thing. And then as we get closer and closer, you see it still takes, it's very difficult for us to affect any real movement of the device, of that bad air, until we get right on top of it. So that pretty well demonstrates the fact that the positive pressure ventilation is much, much more efficient than negative pressure ventilation in ventilating a confined space. It's important to note that the ventilation team does not turn on the fan. They leave that job to the recon team once they've safely left the area. Because once the fan gets turned on by the recon team, any product that is in the space, especially when you're dealing with a space that only has one opening, is going to be forced out of the confined space. So let's watch what happens in our simulation. So clearly the amount of atmosphere, the quantity of the atmosphere coming out of the space is increased. It's critically important that the recon team maintain that respiratory protection until the atmosphere checks clear in the work area with the air monitor. And depending on the size of the space and the volume of air being moved by the fan will determine how long it may take to clear that particular space from hazardous atmosphere. All right, let's take a few minutes and talk about some of the problems or hazards associated with ventilation operations. The first one that we'll talk about is usually not a big concern for us when we're performing rescue ventilation, but it involves a thing called recirculation. And the name of it kind of tells you what the problem is. What we're concerned with in recirculation is the atmosphere that's being forced out of the confined space. If there is an ambient wind or air currents that are going to bring air move the air towards our ventilation fan, the contaminated atmosphere can be drawn back into the intake of the fan and then recirculated into the confined space. Obviously, we don't want to do that because we're just reintroducing the hazard that we're trying to get out in the first place. So we solve for recirculation by placing our blower upwind when it's appropriate, making sure in all cases that the intake of the blower is in clear air, and that may require some additional air monitoring to make sure that we don't have the intake of our fan next to a running vehicle where we're drawing in exhaust, or we have it near another process going on in the facility where it could intake contaminated air. So recirculation is one of the problems, but again, during rescue ventilation, as long as we place our blower correctly, we usually don't have too much of a problem. Short-circuiting is another problem, and short-circuiting's name is also fairly descriptive, and all that means is that the air is not being fully circulated through the confined space, or in other words, we have areas of the confined space that are not receiving the benefits of our ventilation. This is most common when we talk about doing general ventilation, where I'm trying to clear the atmosphere in the entire confined space, and is not our primary concern during rescue ventilation, where I'm simply trying to provide my patient with fresh air. So I'm still concerned with that in the bigger scope of things, but in the immediate initial actions phase of the event, I just want to get fresh air to my patient. Eventually, our positive pressure ventilation will clear the entire space, and we may simply need to redirect the ductwork once we get established to a different direction or a different corner in the confined space to make sure that we're removing all of the contaminants that are in there. A couple of other less significant, if you will, concerns that we have for ventilation relate to other changes we can make in the environment and how the ventilation impacts our patient. For example, in Michigan and northern parts of the country, we have cold weather much of the year, and we can be introducing cold air into the space, which could adversely affect our patient. He may become hypothermic. I probably still want to do the ventilation, but I need to be aware of the effects on that. Other issues relate to the contents of the space. Do I have a quantity of dust, or what we might see maybe in a grain silo, for an example, where I would stir up all that product and actually make conditions in the space worse? Is issues related to the flammable levels in the space. If we happen to come across a space that has an atmosphere that is above the upper explosive limit, when we provide this ventilation, or this dilution ventilation, if you will, we can actually bring that level down into the flammable or explosive range that would increase the hazard. So in those instances, there may still be value in doing ventilation, but I would want to do so probably only after I addressed the control of any ignition sources and potentially had some fire control method in place. The benefit to the patient is still going to be there for fresh air ventilation, but again, I want to make sure I'm not increasing the hazard in the meantime. So let's wrap this thing up. We've talked about the ventilation equipment and looked at how it goes together, the various components involved in that. We've talked about rescue ventilation specifically and how we want to apply that to get fresh air to our victim. We've also spent a couple of minutes talking about the importance of air monitoring in conjunction with ventilation. Ventilation is very abstract unless we can quantify it by using an air monitor to identify what the levels are, and are we making things better, are we making them worse. So it's important for us to do that air monitoring before we provide ventilation to identify the hazard, after we provide ventilation to see if we in fact are achieving the results that we were looking for. And then of course, continuous air monitoring during a confined space emergency is always appropriate to identify any changes to the atmosphere. At this point, it would be good for you guys to refer to the instructions in your handouts and go out, take a look at your ventilation equipment, hook it up, test it, make sure things are working, and make sure you're ready for that next emergency.